Hello everyone, welcome to the post-contest discussion for Leetcode Weekly round 434. This is Jay and let's move to the first problem. The first problem was count partitions with even sum difference. This problem said that we're given an array of integer nums of length n, and we had this definition of partition where partition was defined by an index I between 0 to n minus 1. And basically for this index, the left subarray was all the numbers from 0 to I. The right subarray was all numbers from I plus 1 to n minus 1. That is all numbers to the right of this index. What we had to do was we had to return the number of partitions where the difference between sum of left and sum of right subarrays is even. Let's consider the sample test case for better understanding. Now, if we consider the first question, according to the sample test case, we had this array. So our nums was 10, 10, 3, 7, and 6. All right. So our nums was 10, 10, 3, 7, and 6. Now, what could our I be? Well, our n is 0, 1, 2, 3, 4. So our n is 0, 1, 2, 3, 4. And we had to split this thing into non-empty partitions. So you could split up to 0, 1, 2, and 3. You couldn't split 4 because that would basically lead it, make our right subarray empty. So your I could be 0, 1, 2, and 3. Let's see how these things split the array into left and right. So this is our left subarray. This is our right subarray. When I is 0, up to here, everything is in left. Remaining part is in the right subarray. So your split would be 10, 10, 3, 7, 6. Next, you'd put the next 10 in the left subarray, remaining part in the right subarray. Then you'd put the 3 in the left subarray, remaining part in the right subarray, 7, 6. And finally, you would have 10, 10, 3, 7 in the left subarray and 6 in the right subarray. You couldn't put the 6 in the left subarray and have an empty subarray over here because that was empty subarrays were not allowed. In a partition, you had to add non-empty left and right. What's the sum of this array? It's 10. What's the sum of this array? 10 plus 3, 13 plus 7, 20. This is 26. The difference between 10 and 26, the absolute value is 16, which is even. So this is a good partition. Basically, this partition has to be counted. 10 plus 10 is again 20. So 3 plus 7, 10 plus 1, 16, plus 6, 16. 20 minus 16 is 4, which is even. So this is a good 2. Then you have 10 plus 10, 20. This is 23. 7 plus 6, 6 plus 12 plus 1, 13. 23 minus 13 is 10. This is even. So this partition has to be counted too. And finally, you have 10 plus 10, 20 plus 3, 23 plus 7, 30. And over here you have 6. 30 minus 6 is 24, which is even. So this is good too. So you have 4, 1, 2, 3, and 4 good partitions. So your answer would be 4 over here. And your answer is 4. Now, this is like the similar logic that has been followed over here. And if we just go on and implement this, whatever we have done over here, what we are doing is we start with a split. We have a left subarray, we have a right subarray, and we check if this thing is good. If it's good, increment our answer. Then take the leftmost element from the right part and push it into the left subarray, increment their sums, and just go on doing this thing. So you could do this in this way. Initially, let's just say that the left subarray is empty and right subarray has all the elements. So the sum of right subarray would be sum of all elements, and your result is initially 0. Iterate over all elements from 0 to n minus 1, not the last element because you don't want to make the right subarray empty. Then add this element to the left subarray that corresponds to adding it to the sum, and remove this element from the right subarray that corresponds to removing, like subtracting it from the sum. If the absolute value of difference between these guys is even, basically this is, we are taking the absolute value and it with 1. If this and results in a 1, then it is odd, and the not of it evaluates to 1 when this is even. So, and if it's even, then increment result, and finally we just return the result. So this was one implementation, but there's one more observation that you could take. So this is your array, right? this was like what we discussed right now was like the most straightforward approach. Just one more thing. This is your array. Say you split your array at I. So everything at this part is at left. Everything in this part is to the right. Now, let's just say total is equal to summation of all the numbers in the array. All right. Now, one thing to notice that total always remains constant. No matter how you split your array, your sum is not going to change. And your sum is going to be equal to sum of the left portion of the array plus sum of the right portion of the array. All right. And we have to find the splits where the absolute value of right minus absolute value of left. This guy is even. Okay. Now one number minus other number, this is even. When is this even? So let's just say that your right is even and left is even. Then this subtraction will result in even. If right is odd, left is odd, then this subtraction will result in an odd number. If this is even and this is odd, then odd minus even leads to an odd number. So this is not a good split. Now notice one thing. If right is even, if left is even, then you would have a good split. But in that case, if left is even and also right is even, then the sum of these two things is also going to be even. And if left is odd and right is odd, then sum of these two things is going to be odd, even number. Basically, what we are seeing is total is equal to left plus right. And if left is even, right is even, or left is odd, right is odd, only in these two cases you have a good partition. But in these cases, this would basically force your total to become an even number itself. So, and total is fixed according to our test case. So, only if total is even, then you could have some good partition. If total is odd number, then no partition can be a good partition, because for a partition to be good, the difference has to be even between this left and right. But if that guy is even, it means that either both left and right are even or both left and right are odd. But if both of them are even, all, or odd, then the total has to be even. So, and one more thing, if total is even, so if total is even, and this is the left plus this is your some random partition. If total is even, this basically forces left and right to have same parity. So if total is even, then if left is odd, then right has to be odd. If left is even, then right has to be even. So if total is even, then it forces all partitions to be good partitions. If total is odd, then no partition is a good partition. So basically, instead of this, you could also have something like, if total is even, then your answer is n minus 1, the number of partitions. If total is odd, then your answer is 0. No partition is a good partition. That was one more like slight observation with this problem. Let's move on to the next problem. The next problem was count mentions per user. In this, we are given an array, an integer number of users. Then we are given n events. Each event was an array of size 3, all 3 strings. And we had to count what is the number of basically what is the number of like mentions of this user. First, let's go to the events that are, then we'll get to what the mentions are. So each event had either one of the two types. The ith event can be either of type message event or of type offline event. Now, offline event meant that some user went offline at this timestamp. The user with ID of this event, ID of I, went offline at this timestamp. Timestamp was basically given in terms of seconds. So if it's 30, then it means at 30 seconds. And when this user goes offline, so if a user goes offline at 10 seconds, it also meant that this user will go offline for 60 seconds. So if a user went offline at 10 seconds, then he'll come back online at 10 plus 60, that is 70th second. And we had one more type of event, that was message event. Here we were given this type of event, timestamp, and the mention string. This meant that the mention string can be one of three things. Either it's all means that all the users, irrespective of their online or offline, are mentioned in the message. Here means that all the online users, the users who are not online, are mentioned in this event. And else the mention string could be space separated ID numbers. In that case, the all the users that are mentioned in those ID are mentioned basically. So what we had to do was we had to process all these events, and it was not guaranteed that these things are sorted by timestamp or anything else. And what we had to do was we had to process all these events and find the total number of times each user was mentioned across all events. And initially, all users were online, and if at a certain timestamp some user goes online or offline, that would be processed before handling any messages at that time. Basically, if there are any clashes, then online or offline takes priority. Now, let's go through some test cases over here. So, this is problem B. The first test case, we had two users. We have two users and three events. All right. Just make a table. So you have each event has three things. It has a type, it has a timestamp, and it has some user IDs. The first event is there was a message at timestamp 10 seconds with user IDs ID1 and ID0. Then second type, some user went offline at 11 seconds and the ID of user was 0. Third, there was a message at timestamp 71 and it mentioned here that is basically all online users. Now let's go through these events one by one and we'll maintain the mentions arrays side by side. So our user IDs are 0 and 1 and also online, which users are online and which users are offline. Initially, both users are online and both users have 0 mentions up to this point. You go to the first type of event, it's a message. It occurred at timestamp 10 and it had user IDs ID1 and ID0. So both users with ID 0 and 1 were mentioned. So let's update this. They were 0, 0 and now they were mentioned once. So this became 1 and 1. Next event, a user went offline at timestamp 11 seconds. So the user 0 went offline. User 0 is offline up to he went offline at 11 seconds. So 11 plus 60 is he went offline up to 71st second. Next event is a message. It occurs at 71st timestamp and it mentions all online users. Now the user 0, he was offline up to 71 seconds and now is the 71st second which we are dealing with. So let's first make it online. So this guy is online now and then we basically get mentioned for all active users on online users. Both of them are 1, 1. They would end up becoming 2, 2. So your final answer would be 2 and 2. This is like the final answer over here. And let's look at one more test case, which would basically help clarify the offline idea. Now, if we look at this test case, here again, let's have the type, timestamp, and IDs. Initially, the first event is some user goes offline at timestamp 10 seconds. He has ID of 0. So we have this mentions array and we have this online array. And we have two users. So users 0 and user 1. Initially, both users were online and had 0 mentions. Now, user 0 went offline at 10th second. So he would be offline up to 70 seconds. Like up to timestamp 70, he would be offline. And this guy is offline now. There are no mention up to this point. So this is done. Then we move to the next event. There was a message. It occurred at timestamp 12 and it mentioned all online users. It occurred at timestamp 12, so 12 is less than 17, so nothing, no changes on this side. And it mentioned all online users. So 0 was offline, but 1 was online. So 1 was mentioned one more time. So we get an answer of 1. So your answer at the end would be 0 and 1. That's it. And moving to how you would implement this thing. Now, before implementing, how we would approach this thing. First is that this is a very implementation heavy problem. So there's not really much of an data structure or algorithm thing over here. So first, let's break down into what are the things that we have to do. The first and foremost thing that we have to do is sort the events. Okay. So nothing, it's not given that in the sample test case, it just happened that the events were sorted by timestamp, but it's not given that events will always be sorted by timestamp. So the first thing you do is sort the events by the timestamp. And if two events occur at same timestamp, then prioritize the offline event, like the user going offline event, because according to our question, so according to our question, if there is like any user going offline or coming back online, then that is handled before any other type of event, like the other type of event. So these are the two things by which you sort them. Second, once you've sorted these guys, you need some data structure, like maintain some data structure to handle offline users. Why do we need some data structure to handle offline users? Because offline users can come back online at some time. We need some way to basically handle these guys. And then finally, process all the events in increasing timestamp. That's what we can do. Now, this part, there are multiple ways to deal with this. What I've done is I've used priority queue. You could use a normal queue. Actually, it won't matter. Or you could maintain an array of the last offline time. So there are a lot of things that you could do at this part. And yeah, finally, like basically and finally, once you have this part clear, then you basically go over all the events. At the current timestamp, you just see are there any offline users who can come back online, and finally just update your mentions array. And that would be like how overall this problem would be solved. So let's go over the code. First, this is the function that we were given. We create the mentions array that we have to return, like how many times a user was mentioned. Then we sort our events array. How do we sort these things? First, see is the timestamp same for both of these events. If the timestamp is same, then put the event which has offline type before the other event. If it's not same, then put the event which has lower timestamp, that is it occurred before this event first. Then this part is we could do this thing in many ways. What I've done is we maintain this is online array. It basically indicates is this user online. And over here, I've used a priority queue, but even a queue would work because we are basically iterating and increasing timestamp order. So priority queue of pair of int, the first integer basically means what's the timestamp at which this offline user would go online. And the second means the ID of this user. So this is the offline user's priority queue. And all mention is a variable that we use to have the all mentions. How many times did the all tag occur in the message? Then we iterate over all the events. We take the timestamp. The timestamp is the second element in the event array, and it's given in string format. So you have to convert it into integer that you can do with stoi in C++. In Python, I guess it's a bit more simpler. Then we check at this timestamp, do I have some offline users who are going to go online once again? So who have completed their 60 seconds. If there are some offline users, check the offline user with least back time, like the time to come back. And if it's less than equal to timestamp, mark him as online and remove him from the offline data structure. Priority queue over here, maybe queue. Then then going ahead, process this event. If it's a type message, we have a lot of things to do. If it's offline type, like a user going offline, get the ID of the user. It's the third element in the array. Convert it to integer once again. Then mark this user as offline and add him to the offline user's priority queue. He'll come back online add the current timestamp plus 60 seconds, so you'll be offline for 60 seconds. And this is the user's ID. If it's a message type, if it's an all type, we basically just increment this all mention variable, and at the end of the entire loop, we just add it to the basically all the users, like how many times all mention was there. If it's of type here at the rate here, it means that every user, we iterate over all the users. If they are online, increment their mentions. If they're not online, just leave them as it is. And finally, other than this, what you could have had was you had this form of string where users were mentioned in ID1, ID0, ID3 in space separated template. Now, in this case, what we can do is we can use a string stream to basically tokenize the given string and then process each of the tokens. You could either do this like count number of IDs with number of spaces, or even while scene is okay. One more way would to implement this thing would be while IDs extract into some string. That way would be fine too. What I've done is we have counted the number of IDs over here. That is basically number of spaces plus one. Then for each ID, the string stream basically uh, interfaces the string such that you're in a sense you can in a sense deal with it in C++ as good as you're taking input from some actual user. So you take the ID of this guy, like you take the ID from the string, then this ID, it's still in the string format, so we have to convert it to int. But in this case, the first two characters have to be ignored, basically removed. So starting from 0, 1, 2, starting from index 2, give me the remaining string that has length of id dot size minus 2, that is the number that remains, and convert it to integer. This would give us the id and increment the mentions array, like this id was mentioned, so increment the mentions array. Yeah, that was the second question, very heavy on implementation side. Then let's move to the third question. The third question was maximum frequency after subarray operations. And this, we were given an array nums of length n, and we are also given an integer k, and we have to perform the following operation once. Basically, we could select a subarray I to j, ij, like I is less than equal to j, and both of them are in range 0 to n minus 1. And then we could select some integer x. X could be anything. It is an integer, so it could be 0, it could be 1, 2, 3, 4, any positive number, or it can even be a negative number. And we have to add this x to all the elements in our subarray that we had chosen. And what we have to do is we have to find the maximum frequency of the value of k after this operation. And this is the definition of subarray, that it's a continuous non-empty sequence of elements within an array. Let's go over a sample test case. So we're solving the third problem. Over here, our nums is 1, 2, 3, 4, 5, and 6. All right. And this is our nums, and our k is equal to 1. What we can do is we have to choose, for our operation, we have to choose three things. One is the subarray in which we are going to operate, and the second is the x that we are going to use to that we are going to add to all elements in this subarray. Let's just say that I choose this subarray. And finally, once all of this is done, we want to maximize the frequency of k, but that is, we want to maximize the number of k's there are in this array. I choose this subarray and I add -1 to this. So you get 1, 2, 3, 4, 5, 6 gets converted to -1 is added in this subarray. So this will get converted to 1, 1, 3, 4, 5, and 6. So in the subarray 1 to 1, I add -1. You have two ones, and we can perform this operation exactly once. So we have two ones, and yeah, that is our answer. Something similar happens over here once again, and I'll just copy this test case. In this test case, we look, we have 10, 2, 3, 4, 5, 5, 4, 3, 2, and 2, and our k is equal to 10. So, yeah, what we can do is, in this case, we can choose this subarray, that is I is equal to 1 and j is equal to like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. J is equal to 9. We can choose this entire subarray and add an 8 to it. That would convert our array into 10. 2 plus 8 is 10. 3 plus 8 is 11. 12, 13, 13, 12, 11, 10, and 10. In this case, we get 1, 2, 3, and 4 tens. So our answer would be 4. And there can be many more other operations, but 4 is like the maximum that you can get in this case. So that was the overall problem. Now, how do we approach this thing? Okay. First thing is, whenever we do an operation, first let's look at what are the things that we are getting. We want to optimize the number of Ks after our operation. What are the things that we need to decide on to perform an operation? There's an X, there's an I, there's an J. Okay. What is the range of possibilities for I? I has to be greater than equal to 0, less than equal to n minus 1, assuming that we are like using zero-based indexing. J has to be greater than equal to this thing, I less than equal to n minus 1. And the constraints on size of our array is big of n is up to 10 power 5. So you can't have something like big of n squared right now. We need to have something like big of n into log n, or big of n into something small, or even big of n itself. Now, how do we, so what do we fix? Like when we have such type of things, like we have this operation, and after this operation, we want to maximize something. If the constraints allow, we can go over all the possible operations. If they don't, we try to fix some of the variables that we need to basically pinpoint an operation and try to find what's the maximum value in the overall the other variables in some better way. First, fixing I and j, like if you fix I and j, that would basically mean that you would have to iterate over all I from 0 to n minus 1 and all j from I to n minus 1. Then you fix this I and j and then try to find uh, max k for this operation. Like, and over here you have freedom to choose x. This would lead to a big of n squared solution to some degree. So we can't fix I and j outright. But let's try to see how we can basically, let's try to see that if we have fixed I and j, what my answer can be. How do I, even if I fix I and j, what my answer can be. So maybe if I try to fix x right now, I don't know how do I fix x, because x is any integer. There are an infinite number of integers, so we don't really know how do we fix x. If I want to fix x, I need to iterate over all the x and then try to fix them. But any integer is not a like good way. Like I don't know which integers to iterate on. So we don't know how to fix x right now. We know how to fix I and j, but that would lead to a big of n squared solution. But for now, let's try to see, even if we fix I and j, how do we calculate the answer? And then maybe we will get an idea of how we can try to fix x. Let's just say you have fixed I and j. All right. And consider some small array, say k is equal to 10. Your array is something like this. This is 10, 10, 10 over here. And this is your I. This is your j. There are some number of 2s over here, some number of 3s over here, a 10, and a 4 over here. All right. What is the x that you would choose for this fixed subarray I and j? For now, we have fixed this I and j. We'll in the brute force approach, what we can do is we can iterate over all possible ij and try to fix them. Now we have fixed this ij, and assuming that this is the ij in which I have to do a plus x, what are the values of x that I will choose? Well, I want to maximize my number of k's, that is number of 10. Now the 10 that lie to the left, I'll get two tens anyway. To the right, I'll get 110 anyway. So they are unaffected by whatever I choose. The people that are affected by what I choose are the ones that lie in between. So I can choose 2, 2. So I can choose x equal to 8. That would basically convert 2 into 10, 3 into 11, 10 into 18, and 4 into 12. If I choose x equal to 8, these two 2's get converted to 10. Basically, I get two tens. I get two k's, two tens. Or I can choose to convert these 3's into 10, basically by plus 7. But then I would lose these 2's because 2 plus 7 is 9. Then I would get two tens, like two k's once again. Or I can let this k 10 remain as it is plus 0. In that case, this would remain 10 as it is. But I would get neither these 2's, neither these 3's, nor this 4. So basically what we are observing over is, if your subarray looks something like 2, 2, 3, 3, 10, and 4, you have to choose exactly one number and you get to convert, you have to choose x such that you convert only that number into your k, and everything else, like if you choose 2, then all the 2's will get converted to k, and everything else will get converted to something else that is not k, even including k itself. So if you choose 2, you do a plus 8, all 2's will get converted to 10, but 10, if there was a 10 previously, it will get converted to 18. If there was a 13, it will get converted to 11. 14 will get converted to 12. So basically, when you operate on the subarray I to j, choose x such that you maximize the number of k's. Right. You want to choose x such that you maximize the number of k's. Now, basically, what you can do is you can choose a x such that you want to have maximum number of k's. But prior to applying this x, these k's were something else. And what were these k's? These were this was the element with maximum frequency. So basically, what we do is we take this subarray, get the number with maximum frequency, and choose x such that this number is converted to all k's, and all other numbers are converted to something else. So this kind of allows us to fix our x. So we can choose our x such that the element with maximum frequency is converted to k. So we have maximum number of k's after our operation. Now, this is good when we had an big of n squared approach. So what we can do is for I equal to 0 to n minus 1, for j equal to I to n minus 1, like find frequency of like element with max frequency. Then your answer would be basically maximum of whatever your current answer is, and k's to left. What are the k's that lie to the left of I? Like if there are any k's over here, what are the k's that lie to the right of I? Plus k's to right of I, plus this max frequency that you are getting. Basically, what you say is you convert this max frequency element into the element with this max frequency into k, and all other elements get converted to something else because of that, and you get your answer. Now, this is a big of n squared answer, and we obviously it won't pass. What we need is we need to optimize this thing. Now, we had three parameters, I, j, and x when we were doing our operation. How do we now we tried fixing I and j, and that led to a big of n squared approach. We didn't know how to fix x, but now we have some idea that all x are not on the table. We aren't using all x. We are only using x such that we are converting one of the elements in the array to k. So it's not all x. It's not that all the x, all the possible integers are under consideration. If we try to fix x, x is going to be at most, there are at most n values that x can be. So we have some idea on what we can, if we fix x, on what values of x we have to iterate over. So let's, instead of fixing I and j, let's try to fix x. But if you just fix x, there's nothing like, we don't really know which arrays we have to consider now, all those things. So let's also fix j. Okay. Now you have fixed x, you have fixed j. Fixing x means that there's some number d which gets converted to k. D is actually equal to k minus x. So k minus x plus x will get converted to k. So for ease of notation, we'll just assume that rather than fixing x, we are actually fixing d. So we are fixing d such that d is going to, after our operation, this d guy is going to get converted to k. Now what would our operation look like? All right. You have this array nums, and this is the j guy that we have fixed. So we are going to consider all operation up to this point that end at this j, and they can start at some here or here or here's anywhere. All keys that lie after this j, they are going to be counted as keys. All right, it's good. You have this j, you have this I. All d's that lie in here are going to get converted to k's. So there, you have to count the frequency of d from over here. All k's over here, they are going to remain k's. So you get frequency of k from over here. And all k's that lie before this thing, they are going to remain k's. So you have frequency of k from over here. Now, this I thing, we still haven't fixed this I. This I can be here, 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 anywhere. But we have fixed this j. So we are iterating from j to 0 n minus 1. We are iterating over all the possible values of d. And also one more thing, that here the nums of I is at most 50. So you have at most 50 values of d, and that's something you can iterate over. Now, we don't know where exactly, like, or all the possible values of I, what is the maximum answer that you can get. That's something we want to calculate more efficiently. Now let's look at an optimal answer. Okay. The sample test case. Okay. Yeah, let's look at this test case. Basically, we had k as 10. And we had this array of this form. You have some number of 2s. You have some number of 2s, and finally you have some number of 10s over here. Say that you have fixed your j up to this point, and if you look at it, the optimal I would be over here. Okay. Why? These two tens would remain as it is. There won't be any operation on this. These two tens will remain as it is. There won't be any operation on this. On this part, you would do a plus 8 operation that would convert these 2s into 10s. And the 10 would remain as it is. Like 10 would get converted to something else, 18 or, but it won't be counted. Basically, you would have 2 plus 3 plus 2, that is 7 as your answer right now, for considering that 2 is getting converted. Now the thing is, look at all the numbers that are being added into your answer, like before operation. Like these things got converted to 10, but before operation, what were their values? We look at it, it was 10, 10, 2, 2, 2, up to j, and after this you had some number of tens. Ignore the things that are after j, only let's consider what's up to j. Up to j, you see, you're getting a subsequence. You have 10 some numbers, you have 10 some numbers, you have 10 some numbers, and then after this point you start picking 2 some numbers, 2 some numbers, 2 some numbers, and again 2, and you end at j. Okay, and maybe there may be some more numbers before you end at j, but basically what you have is, you have a subsequence of form 10 10 10 10 10, then you start somewhere at 2, and then you're 2 2 2 2 2, and then you end at j. You basically operate on this part, convert these guys into 10. These 10s remains as it is, and the remaining 10s remain as it is. Okay. Now the thing is, how do you decide this I? Okay, how do you decide this I? We don't need to decide this I. We just need to find the maximum length of such string that you can get up to j. Because we don't want an ij where we want to, like, this is the thing where you have to operate. We just want what's the maximum number of tens that you can get. The maximum number of tens that you can get, now you have reduced it to a different problem. the maximum number of k's up to j, using by fixing that d is getting converted to k and j is fixed, is equal to max length of subsequence that is of form to some k, and then some d, and there can be any number of elements in between over here. That is the thing. So right now what we have is the maximum number of k's that you can get after an optimal operation is the maximum length of subsequence of this form. Some k's initially, then d's, and then you could have any number of k's after j. But we are operating from j to some I, and we'll basically cut off over here and convert these things to k. How do you calculate this subsequence? Well, we can use some form of dp over here. What we can say is my dp of d is max subsequence of this form, that some form of k's, then some d's, ending at j, and dp of, actually you could say dp of jd or 2d dp, but it would be more space efficient to maintain a 1d dp and update it in place. So that you could say this thing, this is dp of d. And now how do you update this dp? So let's just say that you are at this j and you want to go to j plus 1. If you're at this j, then your answer would obviously be maximum of dp of d plus the k's that are to the right. Maximum of all these things will basically give you your answer at this point, assuming that j is fixed at this point. Now you're at this j and you want to go to j plus 1. How do you do that? Like basically, how do you update your dp array? How would that be updated? Now dp of d is your like kind of k. dp of d is basically a maximum length of subsequence of this form. You have some number of k's, some number of d's, and it ends here. Now if j plus 1 is d, you can actually update your dp of d to go to be incremented by 1. Basically you had this k, you have this d, and at j plus 1 you got one more d, so your dp of d got incremented by 1. Or you could have something else. You have this k, you had this d, and you got a k over here, an extra k over here. Now when we say d, it's actually a subsequence, so there can be some k's in between over here which were not being considered because we wanted to maximize this substring. So for example, if you have k, d, d. In this case, to maximize your substring, maybe you just said that I will consider these k's, then I'll consider this d, and d. But now you have an extra k. Now, instead of considering these k, and some number of d's, you can just ignore the d's and have 7 k's. This k, this k, this k. You have these 6 keys, and this is the new key. So you have a subsequence of length 7. All right. Basically, this just means that don't do any operation. Just let the case be as it is. Then maybe you can append some d's from the next thing over here. But basically, like this is the thing. As long as you have a subsequence of d form, that can always be converted to some operation that would give you an answer. And your answer would be the length of subsequence plus whatever case remain to the right. And when going from j to j plus 1, if there's a d, if there's neither a d, neither a k, your dp array would remain as it is because there's nothing being added over here. If there's a d, then you're basically, you could just append that d to whatever subsequence you had previously. If it's not a d, if it's a k, then you have this option that maybe the d's that you're considering, if you just remove these d's and consider the k's in between these d's plus this new k, maybe the subsequence that you get of all k's is bigger than this dd subsequence that you have, and then you can use this all k subsequence to extend it with the d's that come in future. So that was like the overall idea for this problem. Let's go over the code. So this is the function that we have to write. N is the size of array. Remk is how many k's there are to the right of this thing. Result is what is the maximum number of k's you can get. Initially, there are remk number of k's in the array. So you don't do any operation. Not doing any operation is as good as saying pick any subarray and add 0 to it, because 0 is allowed if you had to strictly do one operation. Then we maintain a DP array. Initially, all elements have this subsequence length of 0, because we aren't considering any elements. Then go from like I from 0 to n minus 1, but it's actually like the j we were fixing. Consider arrays that end at I. Consider operations that end at I. Now, if nums of I equal to k, then this guy has actually come to the left of j. So it's no longer in the right. So decrement the remaining k, that is number of k's that are to the right of j. Then we increment nums of I. This is basically this thing over here, because we have got a d over here and we had some subsequence over here. We are just extending that subsequence up to this point. If nums of I equal to k, so we have got a k over here. And now we actually have the option that for all d's, if they were in this form, kkk, some number of d's, it may be more optimal for them to switch from this to all k's. Maybe not guaranteed. So we are basically going to take maximum for each j from 0 to 51. There are at most 0 to 50, like these many possible digits. DP of j is whatever the maximum length subsequence it already is, or convert it to all k's. And finally, our answer would be result is basically I'm ending my subsequence at this point. DP of nums of I is basically this, what is the maximum length of subsequence of form kkk, then some number of d's. I operate on the d's. So we get that k's and the d's both get converted to k's. And finally, what are the k's that are to the right of this thing? They'll remain as it is. So this is like our final answer. We just return it. So that was the third problem. And let's move to the final problem. So the last problem was frequencies of shortest subsequences. In this, we were given an array of strings words, and we had to find all shortest common supersequences of words that were not permutations of each other. What did that mean? First, they defined a supersequence as a string that has all the words as a subsequence in it, and we had to find shortest such thing, and we had to return frequencies array, which basically represented the frequencies of all these shortest common supersequences. So that was it. And a permutation is a rearrangement of all characters of string. So basically, we didn't have to return this shortest supersequences, but rather than frequency arrays. So even if you had some random frequencies, it won't matter. Like even if there were many permutations, so even if ACA was a thing and AAC was also an answer, then we just had to return a frequency array where A had frequency 2 and C had frequency of 1. Let's go over a sample test case to clarify this thing more better. Also, for the above problem, like the time complexity for the above problem was the previous problem was this is big of n into max number of nums of I, and the space complexity was big of max number of nums of I. You could also implement it with a 2D DP for I and nums of I, and that would work with a greater time complexity, like more time complexity. Sorry, space complexity. Now let's look at this. So yeah, in the fourth problem, our first word is AB, second word is BA. A super sequence ABA. This is a super sequence of these two words. Why? Consider AB. Is there AB as a subsequence of this word? Yes, A and B. Is BA a subsequence of this word? Yes, B and A. So this is a super sequence. Is AAB a super sequence? Is AB a super subsequence? Yes. Is BA a subsequence? No, there's no BA as a subsequence. Like you have a B over here, but there's no A after it. So BA is not subsequence. So this is not super sequence. Then you also have BAB as a super sequence, because AB, here's your A, here's your B, a subsequence. BA, B, and A, a subsequence. So these two are the like subsequences. And we had to do was we had to return frequency arrays for these two things. So for the first, the frequency frequency of A is 2, frequency of B is 1, rest are all zeros. For second, the frequency of A is 1, frequency of B is 2, rest all are all zeros. Now, this was the first question. This was like the first thing. The second would clarify the permutation part better. So for the second one, we had AA and AC. So we had AA and AC. Now the thing over here is we need a super sequence. There are two super sequences actually. You have ACA and you have AAC. Is AA a subsequence of this thing? You have AA, yes. Is AC? AC, yes. So this is a super sequence. Is AA a part of this super sequence? A and A, yes. Is AC a part of this super sequence? A and C, yes. Both of these are super sequences, but we don't really need to consider both of these. We just need the frequency array for these things. So the frequency array for both of them, A is going to have frequency of 2, there's no B, so 0, and C is going to have frequency of 1. This is the only thing that we needed to return over here. So yeah, right, that was thing. And important part was the length of words. Number of words was less than equal to 256, and each word had exactly 2 characters, and all words were unique, and also the total number of characters was going to be at most 16. So you have A, B, you have B, C, you have say A, D, and this A, B, and D. You have 3 characters over here. In such a way, sorry, A, B, C, and D. So you have 4 characters over here. You have A, B, C, and D. You have 4 characters over here. This is going to be less than equal to 16. So there's not going to be a case where you have all 26 A to Z characters. You can have at most 16 characters according to the constraints. And all strings in the words are unique. So yeah, that was one part. Now, first thing looking at these constraints is that maybe we can try something on side of permutations, or maybe something we can try on side of exponentially exploring the space. But first, let's try to see what are the what exactly we are doing over here. Consider a simpler version. Say you have A, B, C, B, C, and you have AD. All right. First, each word has length of 2, and there are at most 256. But if you have a length of 2, basically each word says that A comes before B, B comes before C, A comes before D. This points to, like, it would be a very what do you say, intuitive or normal thing to represent this thing with a graph. Okay, AB says that A comes before B, so add an edge from A to B. BC says that B comes before C, so add an edge before C. So in the final string, there's this thing. And AD says that A comes before D, so not AD, I think I should have said AC. Yeah. So add an edge to C. This is like a very simple graph. So in this case, you'll have only like one superstring, that is ABC. ABC, A comes before B, yes. B comes before C, like there's a substring BC, yes. A to C, A and C, yes, it's satisfied. Will AC be satisfied? No, the B and C part won't be satisfied. And basically the frequency array over here would look like A, B, C all have frequency 1 and everything else is all zeros. Consider something else. You have AC, A, B, B, D. In this case, you basically have A to C, A to B, and B to D. In this case, you can have multiple strings. For example, you could have A, C, B, D, or you could have A, B, C, D, or you could even have A, B, D, C. All of these things would be valid because you have A, B, C as a subsequence over here in all of these strings, and you also have a AC as a subsequence. But the common thing in all of these subsequences is that the frequency A, B, C, D is 1 for all of them. And the observation is that As long as there are no cycles, all characters have frequency 1. If there are no cycles, then all characters have a frequency of 1. The problem starts when you have a cycle. So if you have a cycle, say A to B, B to C, C to D, and D to A. And also, when all characters have frequency of 1, you don't really need to go over all the possible strings that can be formed, because we just need the frequency array, not anything else. So in that case, if there are no cycles, then the answer is actually pretty simple. You just take all the characters and assign them frequency of 1. And if you actually want to construct the answer, then maybe you can do a topological sort and start with A, then put in B, C, D, all those things. But if not that, if you just want frequency array, it's very simple. Assign all the characters to frequency of 1. Problem starts when you have what do you say, a cycle. So you have this cycle. How do you deal with this cycle? Let's try to construct the string. Say we start with A. Okay. We need AB, so I added a B. We need BC, so I added a C. We need CD, so I added a D. Now we need a DA. Now, can I get a DA? I actually have added A already, but I need a DA, so I also need to add an A. So I got this one string. Then say we started with B. I need BC, I added C, CD, DA, and I need an AB. I've already added B, but it's not able to satisfy this BA condition. So I need to add one more B. Thing is, to kind of get this cycle, choose any one node, say C, add this C at the start and at the end, and just go on adding all the other elements that are like you basically break the cycle over here and add all the elements as you would do for non-cycle. So you have this C points to D, points to A, points to B, and B points to this thing. Add C at the front and add C at the back. So basically any element that is between this thing, it has like you can go from C to this element. So all these arrows would become valid, and you can go from these elements to C. So all these arrows also become valid. So basically if there's a D over here, you can have C to D, and you can also have D to C. So or both of these arrows by default, whenever D gets added over here, both of these arrows get satisfied. What you can do is when we add C to the front and when we add C to the back, what we are doing is we are taking this graph and sort of just removing this node C. Why are we removing this node C? Because the moment you say that the C is at front and back, it means that all of these edges are satisfied and we don't need to consider these edges. We only need to consider edges that don't involve C. So edges that don't involve C, now we have D, A, and B. And this is a graph without a cycle. So we know that for a graph without cycle, there's exactly one way to deal with this graph. Just assign them frequency wise. D, A, and B will all have frequency of 1. If you actually want to construct it, we just need to find a topo sort and start with the node with like 0 in degree and then just go on processing this thing. But basically putting a node at the start and at the end is equivalent of removing that node from the cycle. And that will allow you to, in a sense, break that cycle and kind of process the remaining graph that remains. Maybe you could have more complicated cycles, this to this to this to this, and maybe even something goes on like this. Then you could say remove this node. Removing this node means that whatever character over here, just add it to the front and back, and go on so on and so forth. Also, this also leads us to one more thing. Say that you have A, B, A, C, something A, D, or anything. Basically, you have A, B, C, D in this thing. If you add something like this A, B, C, D and A, B, C, D, this is equivalent of removing all nodes. This will basically allow you to generate any length to string that you want from using A, B, C, D. So you want AA can be generated. You want AB can be generated. Basically, whatever you want as the first character, choose it from here. Whatever you want as second character, choose it from here. So it's always possible to generate all these words using at most 2 into number of unique elements there are.
All right. But we also want to minimize the length of the string that we have. And we have this thing that if there are no cycles, we know the answer, it's frequency of all ones. If we have a cycle, we have one way of removing basically one of the nodes and just kind of opening up those cycles and then dealing with them. Now we want to find what's the total number of these things? What's the min length? And once we have the min length, all the frequency arrays. All right. Now this is where the constraint comes in play, that the number of unique characters is less than equal to 16. Our problem is only when we have cycles. If we don't have cycles, we know there's exactly one frequency array, that is all ones. If we have cycles, we run into problem because there are multiple choices like we saw over here. You could even choose A, you could even choose C. So what we can do is we can go all the 2 raised to power 16 possibilities that there are. I choose some nodes, basically characters, and put them at front and back. Right. That would mean that they have a frequency of 2. All right. And all others, everything else has frequency of 1. Like all other characters that actually come in there, they have frequency of 1. Then we see that basically putting these characters front and back means that we have basically satisfied all the, in a sense, nodes, all the edges that these guys had to them. For example, if you have A to B, you have A to C, you have A to D, and say some relation over here. If you put A front and back, and say you had something else too, if you put A front and back, and you put all the other elements in between over here, then that basically means that all these edges coming into A, they will be satisfied by the number over the character over here going into A. This would be the edge. Like this subsequence would satisfy that, and everything going away from A, choose this A and choose the character in there, and you'd satisfy that thing. So that's how you would basically deal with it. Also, if you are removing basically multiple characters, so let's just say you have something like A to B, B to A, and some chain over here, some chain over here, and you've removed both A and B. So you now have A twice and B twice. Even in this case, you could actually form all A B combinations that you want. You could have A, you could have A and B, you could have B and B, you could have B and A. So basically, adding a character to front and back means that all edges that are incident on that node are satisfied, and you can that is as good as removing that character from the graph, removing that node from the graph. And we just see the rest of the graph. Can I put all the nodes in between here such a way that using only frequency 1, they will be able to satisfy themselves? That's basically asking, after I remove these nodes that I am putting front and back, the remaining graph, is it a acyclic graph? Are there cycles in the graph? That's all I want to ask to that thing. So let's say we have something like AB, BC, and CA, and we have A, B, C, D, DE, and EA. This will be represented by this graph: A to B, B to C, A to E, A to A to D, and D to E, and E to A, something like this. Thing is, if you remove A over here, will the rest of nodes be able to form something? Like, will they form a cycle? If they form a cycle, then just removing A won't do. So this is an acyclic thing. So basically, what this gives us is, this is one way. Other way would be that you can remove B and you can also remove E. So you would have to remove 2 nodes. Now, what would be the cost of removing just A? The cost of removing just A would be, you have 1, 2, 3, 4, 5 nodes. So all will occur at least one, and A will occur twice. So 5 plus 1, you get an answer of 6. Or you could remove B and E, both of them. If you just remove B, then that would deal with this cycle, but this cycle would still remain. So you have to remove at least two B and D. In that case, your answer would be 5 plus 2, that is 7. Like your length would be 5 plus 2, 7. So basically, this is how we can deal with this thing. So going over the code for this part, what we do is, yeah, this is the part where we have to implement our function. We maintain a vector of int res, and first, because there are only 16 characters at most, we map them to a integer called id, and we also maintain what is the 0th character, what is the last character, and all those things. We iterate over all words and iterate over all their characters. If this character is already mapped to some id, leave it. If it's not, then the new id is the size of id. Basically, this is like remapping the characters to some id in index compression in a sense. And yeah, we just push the index over here. This is our array. And finally, here we construct our adjacency list. We get the IDs of these characters, and we construct an adjacency list from this thing, basically our graph. Then min length equal to 2 into n plus 1. Why? So what we are saying is we are going to iterate over all masks right now, and we want our answer to have, like, we want to calculate the frequency arrays of all super sequences with minimum length. Okay. How do we do that? First, we just say that our minimum length is 2 into n plus 1. Is it guaranteed that 2 into n plus 1 is enough? Well, yes, because if you have A, B, C, D, if you have 4 characters A, B, C, and D, in the worst case, you can have a string A, B, C, D and A, B, C, D that will have a length of 2 into n, and it will construct all possible length to strings that use A, B, C, D. Yeah, because you can choose the first character from here, choose the second character from here, and you basically have A, B, C, D for the first option, A, B, C, D for the second option. So the length is actually at most 2n, but just to be safe, we are using 2n plus 1. Iterate over all the masks. Now, okay, yeah. So actually, I have this should be n plus length of mask to be fair. But what we do is the mask number. So what we say is this mask we iterate from 0 to 2 raised power n minus 1. We say that the bits which are set in mask, these are the nodes that I'm going to put in the front and behind. And these are the basically nodes in the graph that we are going to remove and check if the graph is acyclic. Now, our length of the string would be each character occurs at least once. So that is n plus the number of set bits in this mask. Now, to actually map one to our analogy, this should have been n plus the pop count of the mask, but even just using pop count of the mask works. So just go with, if the pop count of mask is greater than min length, in that case, the current mask would actually, like the super string that we get after the current mask would be greater than the answer we have in our hand right now. So just ignore this guy. Else we check if there's a cycle after removing the nodes in this mask. How do we do that? To do that, we maintain a visited array, and then we just basically iterate over all the elements and try to DFS from them. In the DFS, initially, if this guy is set in the mask, then return true. Basically, there's nothing to worry about because he's set in the mask. So we are kind of removing this node anyway. Otherwise, set the state to 1 and iterate over all the neighbors. If the neighbor is set to 1, that means that the neighbor was visited previously in the current DFS. So in that case, we have to return false. There's a cycle. Else, if visited 0 and not DFS, then return false. If everything works, then this guy has been visited completely, and we just return true that there's no cycle. And if there's no cycle, we return true, else we return false. Now, if there is no cycle after this, then basically we can repeat the elements in this mask 2 times, one at the front, one at the back, and put all other elements by topological sorting order in between, and that would give us our result. If this is less than min length, we basically just clear our result and get a better length answer. And this is just calculating the frequencies for array. The get frequency will basically initialize a result with sort of 26 length array and all the characters that occur in our words, they will be present at least once, and all those that are set in mask, they will be present twice. So one more increment for them. Yeah, that was our result array. So that would be basically how we do this thing. The core idea over here was realizing that first you could construct any all the possible arrays by putting all characters front ones or to the back ones. Then you in the graph representation, our actual problem was not the graph itself, it was the cycles in the graph. How do we remove the cycles in the graph? We can put one character front and back, and that would correspond to removing that node from the graph, basically all edges being satisfied. And after that, we just had to see that after we remove those nodes from the graph, is the remaining part actually like acyclic or not. If it has cycle, then it's still a problem. If not, it's all good. So yes, that was the Leetcode Weekly 434. Thank you for watching.